Thank you guys for all being here. It's a cold Saturday morning, so I appreciate everybody turning out. Like you mentioned, I'm David Richardson. Mic up. All right. So like you mentioned, I'm David Richardson with the LF Radio Lab at Georgia Tech, advised by Dr. Morris Cohen, who unfortunately wasn't able to be here today. But I'm going to be talking about a little bit of my work, a little bit of sort of VLF and LF background, and then a little bit of just general ionosphere information so that everybody's on the same page. So like I mentioned, I'm going to start with just sort of make sure everybody knows what I'm talking about when I'm talking about VLF waves, talking about the ionosphere, talking about plasmas, things like that. And then we'll dive into the weeds a little bit on my work and then sort of bring it back out to sort of what the meaning of all this is. And so I want to sort of start with motivating this with a cool picture instead of the traditional motivate it with why we care about the problem, things like that. And so this is the ionosphere, sort of recombination of ions resulting in photons being emitted over the Earth. And that's where you see this sort of air glow effect, which is just a really cool phenomenon that I think I sort of want to highlight because there's more to just sometimes things are cool and we want to look at them and not just because they're useful. But to get a little more in depth on what the ionosphere is, it's a region of sort of plasma around the Earth, roughly 60 kilometers and up. Some people set the cutoff at 500 kilometers. Some people say maybe it goes to 2,000 kilometers. It's a little bit wishy-washy at the top end. But sort of ideally, we think of it starting at roughly 60 kilometers where we have sort of ionization starts happening from the sun sort of interacting with the upper atmosphere. And that moves all the way up to sort of satellite altitudes where the ionosphere can sort of directly impact satellite. And so here on this plot on the right, we're looking at electron density. So if you think of an ion as some positively charged thing and an electron, in the Earth's ionosphere, we can sort of look at only the electron density and treat that as a proxy for how much ionization there is in total. So you see there's three regions here. So those are the D region, E region, F region that is entirely dictated based on sort of what dominant physical phenomena are occurring in each region. And so my work in particular, I'm looking at the lower ionosphere, so particularly the D region, but all these are sort of very critical for a lot of infrastructure. And then we're going way back to elementary school, middle school, sort of states of matter here, just to make sure everybody sort of knows what I'm talking about with plasmas. So you sort of have the traditional solid, liquid, and gas, but if you keep adding energy, eventually your particles will split into a positively charged and a negatively charged ion. And that's when you get to the sort of plasma state. And another way to look at that is sort of, you have this web of positive charged particles and negative charged particles that are always interacting with each other. So if a negatively charged particle starts moving around, say there's some field that's causing it to shift, that's going to sort of have a carry-on effect to all the other particles nearby just because of sort of electromagnetic phenomenon. And generally within the ionosphere, we're talking roughly neutral in terms of same number of positive, same number of negative charges. And so it was sort of just a thing to keep in mind when we're talking about the ionosphere. So what does that mean for radio wave propagation, which is sort of why we're all here? We're interested in radio waves, at least broadly speaking. So if you're in the sort of gigahertz regime where you're talking to satellites, things like that, that can generally propagate through the ionosphere. So it's not quite heavily ionized enough to inhibit the propagation, but it does have some propagation effects. So you think of things like GPS scintillation, things like that. Those are largely driven by features in the ionosphere. However, if you go down to megahertz, kilohertz type range, you get some pretty serious bending or even almost reflections or pure reflections looking and down in kilohertz, where you see the kilohertz waves, which maybe people don't think of as who uses kilohertz waves, but they do have their applications and they are very, very efficiently reflected by the lower ionosphere. So this slide hints a little bit at where we're going with this talk, but this idea that we have some VLF transmitter, perhaps maintained by the US Navy, that reflects very efficiently off the sort of bottom edge of the ionosphere. And then there's also lightning emissions. So if you think of a lightning stroke, we have a very, very heavy or strong impulse of current over a very short period of time. And that produces a relatively broadband frequency response. If you think back to sort of Fourier theory then the shorter the impulse in time, the wider the frequency band is. And so when a lightning stroke occurs, we get a massive amount of current over a very short amount of time, and we get a frequency band up to sort of VLF, LF, so think of 200, 300 kilohertz, all the way down to very low, so like tens of hertz even, although most instruments don't go down that low. But so this gives us two sources of information, where one is very narrow band, so very narrow altitude range that we interact with, but also a very broad band frequency, so we get an idea of how the ionosphere responds to a broad range of frequencies. Now, all that said, if we can't measure it, it doesn't matter. So we do have a measurement device at Georgia Tech called the VLF Awesome receiver, which is two loop antennas, one north-south oriented and one east-west oriented, so we get the sort of those polarizations pretty easily. More recently, we've developed an E-field receiver to sort of complement that and get the Z-field component. So we have a 3-axis receiver. And there's papers and lots of things if you want to read all the nitty-gritty details about it. But the moral of the story is we can measure these things. And what do those measurements look like? So if we pull up the spectrogram, I'm sure a lot of you are familiar with this, but if you're not, it's how does the sort of measured wave look versus frequency and time on the x-axis. So you'll see two dominant features here. You'll see the very strong horizontal lines, and those are the VLF transmitters. And those are very consistently available. Like I mentioned, they're maintained by the US Navy generally, and the Navy doesn't want their communications going down unless they know about it. And so you'll see in that very top, which is in LK, so we're in the west coast of the United States. And so they have a very, very strict time schedule for maintenance, and it goes down, in this case, 14 seconds after the 8 a.m. shift starts, and then it comes back up 8 hours later. And that happens once a week. Very perfect schedule. So these are massively consistently available. The other phenomenon you'll see is these vertical sort of lines, and those are the spheric emissions. So whenever a lightning stroke happens, there's a radio atmospheric, which within the community we sort of shortened to spheric because that's too many words to say. But this is a time domain view of what that looks like. So you see very, very narrow time window that the spheric is occurring over. We're talking 0.0005 seconds. So it's tens thousandths of a second, basically. And that gives us that very broad frequency response that we can measure. Now, this is a sort of the idea that we care about the D region. We do because of these propagation effects. But a lot of times when you think of, oh, we would like to know what the value of electron density is at some altitude, you say, okay, just measure it. What you can do if you are in the F region, so basically the higher you go, the more likely you are that there is satellite availability. And satellites can get down to 160, 150 kilometers-ish, which is well within what you need to measure F region electron density. And if you care about sort of the upper atmosphere, so below the ionosphere, you have access to high altitude balloons. You can think weather balloons. There's a lot of easy access to measurements that way. However, in the sort of D and E region, we're really limited on sort of direct. We put an instrument in that location and took a measurement type methods. We do have access to sounding rockets, but if you imagine you want to take a measurement over the entire United States for a 24-hour window, you're talking launching millions of rockets in a bunch of different places, and you quickly run out of money and support. So we sort of have this measurement gap. And that's where my work on remote sensing, in particular for the lower ionosphere, comes in. So like I mentioned towards the beginning, VLF and LF reflects very efficiently off the lower ionosphere, and that forms what's known as the Earth ionosphere waveguide, which basically allows all of these VLF and LF waves to propagate over global distances. And as they're propagating, they're interacting with the ionosphere, and their waveform is changing a little bit every time it sort of reflects or interacts. And what that does is it lets us look at, if we just measure the amplitude, in this case of a transmitter in Maine to a receiver in Delaware, that we can see a very obvious day-night transition. So as the daytime occurs, the sun comes out, the ionization increases because we have a bunch more solar radiation. The nighttime happens, we lose the solar radiation, recombination occurs, electron density goes down or ionization goes down. And that affects our measured amplitude of our received signal. And we see a very, very strong trend here. Additionally, we see that on April 2nd and April 3rd, there were some solar flares. So I think a solar flare is a massive influx of energy basically into the ionosphere and the upper atmosphere. And so that affects the ionization levels. And again, we see that same trend in our sort of measured amplitude. Another sort of interesting phenomenon is gravity waves. So not gravitational waves that you think of for Einstein's theories, but we're talking gravity waves. So basically, if you throw a stone into a pond and you see that rippling effect, that's a gravity wave. So basically, a gravity wave is any sort of ripple in a fluid. So the same thing happens you think there's some vertical draft in the air currents, and that sort of causes a shift either up or down of ions, and then that sort of ripples out over sort of a very large spatial area. And you can see that sort of periodic, almost sinusoidal rippling is exactly that. We're seeing a gravity wave in our measured data, in this case caused by a hurricane off the coast of Puerto Rico or Arecibo. Buttons. But we have all these measurements. We can say, okay, we observed this in our measured data, but we want to be a little more quantifiable or a little more objective with how we sort of look at what we want to know actually what the electron density is. And to do that, we turn to machine learning. So I think Google and Amazon and Netflix are all doing a bunch of machine learning stuff, but we can apply that to VLF and the ionosphere as well. And so in this case, we're using training data. So we don't have measurements. So instead, we synthetically generate a bunch of random but still realistic looking ionospheres that we use as sort of a way to train the model on a broad range of potential answers. And then we can pass in our real data that we have from our VLF transmitter measurements at all of our receiver sites around the Southeast, and produce electron density predictions for those locations. And so that's what this is showing here. On the left panel, you are seeing H prime, which is basically we have, in order to predict these measurements, we parameterize them with an H prime value, which is basically how high is the ionosphere. It's just some reference height. And then a beta value, which is how quickly does the ionosphere electron density change with altitude. So you can see we have very obvious sort of diurnal variation. So this 14 UT is sort of when the sun rises, and this 22 UT is when the sun sets over our sort of receiver area. And so you see in the morning, the relative ionization is relatively low. The ionosphere is higher. As you get closer to noon, the ionization increases. We get closer to sort of maximum ionization within the day. The ionosphere moves downwards. And then again, the same sort of opposite happens as you get closer to nighttime. The ionization falls again, and we move into a nighttime environment. We also see very clear seasonal variations. So we see summertime, there's more sun than there is in winter. So same sort of opposite phenomenon happens. And then we do see the fall and spring are sort of a little bit weird here. And that could be due to a variety of things. But what we believe most likely is that we sort of have a non-unique inverse problem. So two different H prime and beta values can result in the same measurements, but that doesn't mean necessarily one or the other is wrong. It's just that we don't have a measurement to sort of collaborate that against. We can do the same thing at nighttime. In this case, only doing summer and winter, just to cut out those weirdness that are happening in spring and fall. But you see nighttime is much flatter because you don't have that sun angle changing over the course of the day. The sun is sort of always hidden behind the earth. And so this is a very promising result that we're able to make these things that are mostly in line with what we believe to be happening for both daytime and nighttime environments. And then I want to call back to that gravity wave phenomenon that we observed with Hurricane Maria, but in this case, look at Hurricane Irma, which was a more sort of inward or more inland hurricane that went up the west coast of Florida and then through Alabama. And this is measured in Kansas, so a good ways away. But we still see that if you look at the blue and red lines, they're very, very smoothly varying. So those are before and after the hurricane. But if you look at the green and orange lines, you're seeing very, very massive disturbed conditions due to this hurricane gravity wave. And so that's just a sort of interesting phenomenon that we're observing, that potentially these types of measurements could be used for hurricane monitoring and things like that. And then another, like I mentioned, we have this sort of VLF transmitter idea where you have this narrowband transmitter maintained by the Navy as a source of VLF. And we also have lightning. But as you can imagine, lightning is a natural thing, so it's much less of a controlled environment. So you're dealing with random locations, random time windows, things like that. And so in order to get accurate sort of predictions of what electron density might look like, we have to do a lot of pre-processing first. And so this work is done by a former PhD student in the LF lab to basically take a cluster of lightning strokes. So think maybe a lightning storm is happening in Puerto Rico or in the Southeast US or something. And we can sort of create a representative lightning stroke from all of those to sort of move out a lot of the noise and get a much more clean signal, which is what you can see in this sort of transition from extremely noisy, unprocessed, slightly less noisy, but still not very nice, to a very, very clean lightning stroke looking thing that we can measure and sort of use going forward to predict what the electron density might look like along that path. And so why would we actually care about using lightning at all? So here is this IRI profile. So if anybody's familiar with the ionosphere, it's sort of a general profile that you can use for if you just want to know what the ionosphere kind of looks like, especially at the lower altitudes. But it serves as a good function here for if we only have access to the sort of narrow reflection region that we have with 25 kilohertz transmitter, maybe we can get a sort of log linear fit. So we have log of electron density on the x-axis. So we're looking at basically a linear fit here. And it fits very, very well over that reflection region. So as you'd expect, if you have a measurement of a narrow region, you can fit a linear curve there, and it'll probably fit pretty well. But as soon as you move outside of that narrow fit, the fit moves off the actual line very, very quickly. However, if we have a sort of full VLF spectrum measurement, so things up to 30 kilohertz or even beyond that, we can fit a much more complicated profile to that. In this case, introducing this split here to effectively provide a better fit to what the electron density actually is in real life. And that also provides a better fit to the profile over the sort of altitude range of interest that we have for the D region in particular, which is roughly 60 to 90 kilometers. You can see that the linear fit starts deviating from the optimal answer at roughly 70 or 75 kilometers, whereas this 4-parameter model starts deviating at 85-ish. So we're performing much better when we include this sort of wider frequency range that we get from spherics. But those are sort of two different approaches to the same problem of, so we can fit with VLF transmitters on some path, we can fit from lightning to receivers on some path, but the sort of historically, those have been two totally separate fields. So there's been people who are interested in how do VLF transmitters propagate, and there have been people interested in how do spherics propagate. But the culmination of all those decades of work are that we have basically two different techniques that are totally independent of each other, producing outputs in the same format. So we have VLF transmitter to receiver path average measurements now. We also have lightning to VLF receiver path average measurements using totally different techniques, but producing the same output. And that comes up with how can we unify those models together? And the idea here is to use what's known as tomography. So that's the same type of tomography that's used in a CT scan. So if you go to the doctor and they're trying to take an image, you get a CT scan. The idea is you have some emitter and some receiver, and you get some path measurement from how that wave propagated. And you can sort of back out what the image is underneath, like sort of underlying condition, whether that's an image of your body or what the electron density is over the United States. And so the idea here is we have a bunch of transmitters, the lightning in green or the VLF transmitters in blue. We have a bunch of receivers, which are the red stars. We can just use tomography to make a map. And that's what this looks like. So in the bottom left, we're exploring this in a totally synthetic environment. Because again, like I mentioned, we don't have measurements. So we want to make sure that our stuff is working reasonably well. So we take basically a random sampling of lightning strokes and a random sampling of receiver locations, and then create a random ionosphere, do all the tomography, and then look at percent error. And that's what you see, this red outline here, which I believe is the location that we got below, I think it was 10 or 15% error, which is quite good, especially considering this is basically the only 3D mapping of technique that we have available to us. And so we can say with confidence that our sort of method of tomography over the sort of Gulf of Mexico and the Southeast US is producing measurements or inferences of electron density with good accuracy. And that's what we do here on this right-hand panel. So this is if we take actual measurements in real life and map to sort of the Gulf of Mexico and Southeast US, we get a map of electron density at any location, latitude, longitude, or altitude variable. And in theory, this sort of can expand infinitely outwards. It just, as you go farther away from this region, the error increases. And we sort of have a mapping of what that error increases as a function as with this synthetic case. And as you can see, we have sort of a bit of a ledge here, which is exactly what we would expect with that 4-parameter model that we saw earlier, that sort of idealized view of the ionosphere. And that shows up in the daytime. At nighttime, that falls away, which is again in line with prior research that shows that sort of as you move up in nighttime, the curve sort of shifts and you move outside of that ledge region. So the ledge region actually occurs sort of higher up in the ionosphere as opposed to what we see here. And then as you look here, we see the nighttime is sort of much more wobbly or wavy. And that's the same sort of phenomenon, which as the sun falls away, you sort of introduce a bit more, not real noise, but sort of it looks noisier to a human because we have a lack of that driving solar effects. And so now I'm to get back to the beginning of motivating the whole purpose of this with who actually cares about this. So as you can probably know, the VLF, sort of the lower frequency you go, the longer the wavelength gets. And what that does is say, as you increase wavelength, your effective skin depth also increases. So if you want to talk to a submarine in seawater, which is quite conductive, you need a very long skin depth. The same thing goes if you want to communicate through a very, very thick piece of land, say deeply underground, then you need that sort of long skin depth. And that's why the Navy cares, because the Navy wants to talk to their submarines. And so they build massive VLF arrays, or in this case, just a single antenna to transmit at 24-ish kilohertz, which if you want to do the math is a wavelength in the kilometer range. And this is thousands of acres. So it takes up an entire peninsula in Maine. So massively expensive to build. But the Navy really wants to know that if they have this massively expensive, massive antenna, and they want to talk to a submarine, they want to know what that propagation path looks like. And that's entirely dependent on the D region, which is what we're studying. And there's no way for them to measure that. So that's why they care about our research. And then there's also the lightning side of things, right? So if we can tell you where a lightning stroke occurs, then there's a lot of information there about like thunderstorms, things like that, that are very interesting to know. And there's a company called Vaisala that's doing exactly that. So they have a network of basically the same type of VLF receiver that we're maintaining. And they can do basically time of arrival estimates to sort of geolocate lightning within a very, very small range. I don't know the exact numbers, but it's very, very accurate. And this map in the top right is sort of global lightning over a few years of sort of where we expect to see lightning. And this is all taken from VLF measurements. So we have historical lightning data now available just because of these sort of VLF propagation effects. And this is really important because lightning causes hundreds of millions or even billions of dollars worth of damage to infrastructure every year. So we care about that a lot. So whether you're the Weather Channel trying to say, what does the sort of weather forecast look like? We need to know where lightning occurs. Or if you're an aviation company or ground or air traffic control saying, hey, don't fly through this thunderstorm because you might get struck by lightning, and planes don't like getting struck by lightning, as you can imagine. Or even if you're Georgia Power and you want to say, send out your trucks in advance to be closer to potential repair sites if there's a lot of lightning and causing sort of power line failures, things like that. So there's a lot of companies who are really interested in knowing sort of where lightning is occurring, which is exactly what we can do with VLF. Sort of carrying on that concept of the power grid caring a lot about our measurements. If you think of a power line operating at 60 hertz, that's within our receiver sort of operating range. So we can get down to 60 hertz is a little bit low. We can get down to 200 pretty easily. But you can see a measurement here of taken outside of a power station of the sort of 60 hertz and its harmonics. And you can see we can sort of actually measure the current going through these power lines. And Georgia Power can also measure that with their fancy instruments that they have sort of spread around all their power stations. But if you imagine there's some bad actor trying to cause damage to the power grid, we sort of have this inbuilt random sort of seeding of these lightning strokes that allows us to validate our measurements at any point in time that cannot be faked, because we have sort of Mother Nature has decided that this is the measurement, and you can't just pre-measure what lightning is going to happen. So we have a non-fakeable method for measuring power grid levels that we can send to the power companies and say, hey, whatever you just received, this is what's actually going on. And then there's the whole space thing. So space is a massive topic with a lot of billionaires deciding that they want to launch things to space recently. And so things like satellite failures are quite costly. I don't know if you remember, but SpaceX a little bit ago had 40 or so satellites fall out of orbit just because of a sort of increased ionization due to a geomagnetic event. And that's something that we can sort of observe. So our ionosphere is heavily influenced by geomagnetic storms, things like solar events. And so if we can sort of measure that and potentially forecast things like that using our VLF, then we can sort of help prevent that. Also, we have measurements of sort of ionization levels in general for things like GPS. And then again, the sort of air traffic stuff and power outages, things like that. And the reason that's so critical for understanding from a science perspective even is that everything within the sun-Earth environment is highly coupled. So the sun has a direct impact on the ionization in the upper atmosphere, the ionosphere really, but also the Earth sort of has its own processes such as lightning, which can emit energy up into the radiation belts to cause sort of electron precipitation. So the sun sort of increases radiation in the radiation belts. Lightning on Earth's surface can sort of couple into the radiation belts and remove some of that radiation to sort of balance out this ionization process going on within the radiation belts. And it's all a coupled system that we can sort of study from the ground using VLF or other methods. And then to get a little more sombering to conclude, I want to talk about two geomagnetic storms. The first one is a little bit more minor, but in Quebec in 1989, there was a massive solar event that led to a geomagnetic storm that caused power outages within Quebec for about 9 hours in the middle of winter. So if you imagine you're in Canada, somewhat even northern Canada, and your power goes out for 9 hours in the middle of winter, it's going to get very cold very quickly. So this is a big problem. And the reason this happened is there was a lot of energy being input into the system by the sun, which caused a lot of energy to be input directly into sort of power systems and caused massive current surges, which literally blew up transformers. And not the little ones on the poles, but the big transformers that they have in sort of substations and things like that. So this caused massive amounts of damage, lots of economic damage, as well as sort of your power's out for 9 hours in the middle of winter. Also, it caused a lot of satellite problems. So this chart in the bottom, you see the yellow line is sort of when the geomagnetic event occurred. And then immediately following that, because that introduced so much change in how the satellites propagated, we lost a bunch of satellites, on the order of thousands of satellites over the following few days. And that's a massive loss to whoever's maintaining those satellites that we no longer know where thousands of satellites are. And then the real scary one is the Carrington event, which happened in the middle 1850s, which caused so aurora. So think the northern lights, which you go to the Arctic Circle to see, was visible down in South America. So that's a massive amount of energy being input into the ionosphere, but also into telegraph lines. So they're much less electronically driven back then, but they did have telegraph lines. And just through telegraph lines, the coupling of the energy into those caused massive electrical fires across the United States and around the world. And the idea of if that event happened today, we're talking trillions of dollars worth of damage, wide-scale power outages across the world, probably on the order of a decade to get back to where we are today, plus whatever is just simply lost due to issues along the way. And there would be estimated within the United States, at least 130 million people would be affected by this. And that's quite a sizable chunk of our United States population. So it's not something that's going to just blow over and it won't bother you. And so this is sort of a once in 500 years-ish occurrence is what the current estimates are, but obviously the smaller rate of occurrence you get, the less likely it is to estimate on the dot. But this is something that's going to happen, maybe not within our lifetimes, but not too far away. And so it's something we need to be able to prepare for, but also to be able to potentially predict so that we can sort of make intelligent preparations. And with that, we'll open it up to questions.
Questions from the audience? Yes. Speak up just a little more. Speak up.
You're going to have substantial ground wave propagation in addition to the skywave propagation that you're interested in. How much of a challenge is it to subtract that out when you're making your measurements?
Yeah, so it's not so much that we directly subtract it out as that we use a mode solver when we're doing the sort of forward estimation. So when we're saying, if we know this is the ionosphere and we want to say, what does the transmitter to receiver path measurement look like? We use a full mode solver, which is solving both the ground wave as well as all the upper order modes to sort of say, what should we measure? And then we can compare that to our measurements directly instead of trying to sort of pull out only the first order mode or subtract out the ground wave, things like that, to sort of avoid that problem by just coupling it in with all the other aspects of the measurement instead of trying to pull out one particular mode.
Another question? Yes. Hold on, John.
So, David, there's been a lot written about the Carrington event, but what I don't quite understand is what we can do about it, right? So I think the implication in your research is this would be more predictive, and then parts of the grid could be shut down and shorted out or whatever to protect those mega transformers, which take 3 to 5 years to replace from South Korea. So could you elaborate a little bit on how to protect and if your predictions you think will be accurate enough?
Yeah, so the idea is, like you mentioned, sort of we can potentially shut down the power grid, things like that. And I would say in our current state, we do not have the prediction capabilities. But the sort of an idea behind our lab, as well as sort of the VLF and LF community in general, is that we're progressively getting better at sort of monitoring, not just from the ground perspective, but also from, we can look directly at the sun and say, okay, what do we think the sun is going to be doing in a week or 2 weeks or 3 weeks, and sort of model all the way from the sun through predictions of solar wind or solar flare, coronal mass ejections, all the way to the sort of upper ionosphere and how that couples down into the lower ionosphere, and sort of ideally, hopefully, within the next couple of 100 years before we have to deal with one of these sort of massive events, that will have a much bigger, clearer picture of the sort of entire process so that we can make better predictions. But that starts with, we need an accurate way to model each little layer individually before we can sort of couple everything back together.
Time for one more question. I do have one, Mr. Richardson. You seem to be implying that we're about to head into a new era of using VLF, which is great. Do you think that we'll go back to using, for example, Project Omega type installations in future years?
It's really hard to say. I'm not the one controlling all the money. And that's the big problem with VLF is building transmitters is a massively expensive project. So like I mentioned, there are thousands of acres, and to put that in context, that's thousands of football fields, basically. So building one of these is not a small project. And so it's really hard to say, all these massive funding agencies, are they willing to put in a bunch of money into solving a sort of, we're still a niche problem, but it's an important problem in my opinion. So the answer to your question is I don't know. It's hard to say.
In which they're able to make that consideration.
Yes.
Let's thank our speaker one more time.